This video will be a detailed look at the position function x of t equals t cubed, take away 6t squared plus 5. And the constraint that we're going to put on that is when t is greater than or equal to 0. So what we've got here is a table drawn up with different values of t. And what we're going to find is x of t, x dash t, and x double dash t for each of these values of t. So we're going to find out its position, its velocity, and its acceleration. And what we're going to do is talk about how or what is happening with the particle in question. Okay, on this graph as well, you can see here I've got the position function. So this graph here is x of t, like the thick line. Then we've got the first derivative, okay, that's the velocity function. So we've got position, that's the solid one. First derivative is the velocity function, and the second derivative is the acceleration function. Alrighty, so let's go ahead and define this function on our calculators. So we'll go a shift 7 for define, f of x equals x cubed, take away 6x squared plus 5. Whoop. Take away 6x squared. Give that a go. Okay, so the way we'll do this is we'll got f of x here. Then we've got diff, so we'll go a shift minus for diff, f of x, and we've got a diff ants, so that will get us the double derivative. So we've got all three of our derivatives here. Now what I'll do is grab that one. I'm going to go with x equals 0. So I'm going to get it to do all the substitutions for us. Grab the first derivative, the velocity function, with x equals 0. And finally grab the acceleration function with x equals 0. Let's pop in those values into our table. So we've got 5 is the position, 0 is the velocity, and negative 12 is the acceleration. Alright, so what's happening here? So the position is 5, okay, so we're going to say that its position is 5 to right of origin. Alright, its velocity says that the direction of motion, there is no direction of motion, that is, it's stationary. 0 velocity. And this negative 12 suggests it's accelerating at 12 meters per second, or centimeters per second, or units per time. So what we can have here is actually we can have 0 velocity and some acceleration. And that's hard to understand for some students. They think that if there's 0 velocity, how can there be acceleration? And to that end, I'll just sort of say, imagine a car sitting there idling at the lights. To get the car moving, what you do is you need to push the accelerator. That means to go from stationary, you need some acceleration at that point to start moving. So we can actually have 0 velocity and non-zero acceleration. Okay, so we're going to say stationary, accelerating at 12 units per time, whatever it is. Right, describe the particle motion between 0 and 1. Okay, so let's find out what's happening at 1. So I'm just going to go back to my calculator, type in 1 there, and hit enter, type in 1 there and hit enter, and type in 1 there and hit enter. So a really quick way of just substituting values into all of them. -9, -6. Alright, so what we've got here is we've got from 0 all the way to 1, we're moving towards the origin. Okay, so here I'm going to say direction. Okay, so moving. So this negative sign on the velocity means we're moving to the left. towards the origin. Okay, so we're starting to the right and we're moving left according to this negative sign on the velocity, and we're going to hit the origin, and we actually get to the origin at time 1. Okay, now what is happening with the acceleration? So what happens is if the acceleration, the rate of change of velocity, matches the rate of change of position, that is, they're both negative, that means that what we're doing is we are speeding up. Alright, so what happens here is we've got these matching signs here, which means that we've gone from stationary, we're accelerating, and we've got a rate of change or a negative rate of change of position with respect to time, and we've got a negative rate of change of velocity with respect to time. So that means that we are speeding up. Okay, let's go between 1 and 2. So what happens next? So what we've done so far is we've looked at what happens when the particle gets to this point here. Now we can see what happens is we're going to continue moving to the right. Okay, so let's just get all our values. So 2 is the one that goes in. 2 and 2. Let's just copy that into the table. So negative 11, negative 12, and 0. Alrighty, so what we can see here is between these values here, alright, what we can see is this negative 11 means that we end up to the left of the origin. So its position, we're going to say continues to move left because the velocity is negative. So continues to move left until at, 11 units left of origin. Right, what about its velocity? Okay, so we've got a velocity of 12 meters per second in that negative direction, so that tells us the direction of motion. Now we're going to note something, that at point 2, okay, its acceleration is 0. Okay, so it's not accelerating at all. Okay, so how do we interpret that? We just say it has 0 acceleration. Okay, so here what we've commented is the direction of motion, and that is based on the velocity, okay, and also commented on the acceleration. Okay, so what's happened is we've sped up, okay, and I believe we'll have continued to speed up, but what will have happened is that this acceleration here would have, instead of being -6, would have just gone down further and further and further, or up, I suppose, if you want to consider it, or closer to 0 anyway. So that means that it's not accelerating as much, is what that suggests. Okay, so let's take it from 3, or from between 2 and 3, I think we go from now, 2 to 4. So we're going to go all the way down to here. Right, so let's get 3 first of all. So we'll type in 3, 3 and 3. So we've got -22, we've got -9, and we've got 6, and we've got 4, 4, and 4. Okay, so this one here is what, -27, 0, and 12. Alright, so how do we interpret this? So what we can see here is at 3, we've got this opposing sign for velocity and acceleration. Okay, and what's happening here is this opposing signs actually means it's slowing down. So when we get opposing signs on velocity and acceleration, what we say is we're slowing down, not speeding up, we're slowing down. Okay, so what's happening here is the particle between 2 and 4 is moving left still, okay, because we've got a negative velocity here through to this value here, 0. So it continues to move left, okay, until stationary. Stationary. So it continues to move left until it's stationary. Right? And in this case here we can see that the particle changes direction. Okay, so what's happening is it continues to move left, and is stationary. All right, and what happens here is, in terms of its acceleration, we say that the particle is slowing down. Okay, so we've got these opposing signs here, which suggest that the particle's slowing down at time equals 3 until we change direction. Okay, so the change direction means we've got a 0 velocity. Now note here that we actually have now a positive acceleration, and that again will be something that students will go, how can you have the 0 velocity and an acceleration? So I'll go on to try and explain that to you. Okay, so let's again just make sure that we've got this one. So we know that the particle is slowing down. Now that should make sense, because when you change direction, just say you're doing the beat test and you come into the cones, what would happen here is if you're about to change direction, you can't change direction at full speed. Well, you could try it if you wanted, but what you would do is you would slow down. Okay, so you would slow down. So here we're accelerating away to 2, and here what we do is we start to slow down and then we change direction. And what we can see here is I predict that as I come out of 4, and what we're going to do is check out what's happening here, that what we're going to get is a positive velocity and a positive acceleration. Okay, so the particle, or if we're doing the beat test, we'd be moving right. Okay, and what needs to happen out of a stationary point is I need to accelerate in the same way or the same direction as my velocity. That means I need to speed back up again. Okay, so what's happening here is we're speeding up again. All right, let's get the values for 5 and see what happens. 5, 5, 5. Okay, so what we can see here is that we've got -20, 15, and 18. All right, so we know we're to the left of the origin. The positive velocity suggests we're to the left but moving right. Okay, so between here and, or the final value, we're going to say we move right. Okay, so we're left but we're moving right. And these paired off signs here, positive velocity and positive acceleration, means that we're speeding up again. So move right, speed up. Close brackets. So we're moving right and speeding up. Okay, so here what we were doing was we were coming into the stationary point at 4. So we're moving left until we changed direction, and we were slowing down because of the opposing signs. Here we had matching signs, which means that we move right and we're speeding up away from the stationary point. Now, how can you have 0 velocity here and an acceleration? Well, again, if you think about it, how do you actually get yourself moving? Again, you're at the line, and what you do is you've got some acceleration to actually get you moving. So from that stationary point, again, imagine yourself like a car with an accelerator. What you would do is depress the accelerator to get yourself moving, to allow you to increase the rate of change of velocity with respect to time. Okay, so what you would be doing there is accelerating. All right, so this one here, the point here is the x-intercept, which is this value here. So what I can see is we're accelerating away, and we're going to get to this point here, which is back to the origin. Okay, so I'm just going to sub that last value in. Oops. Plus 5 over 2. Okay, so that makes sense. Okay, so we'll just do this to 1 decimal place. So 0 means we're back at the origin at this point here. We've got 32.6 to 1 decimal place and 23.1 to 1 decimal place. So again, we're back at the origin and we're still speeding up, okay? And the fact that it's positive, we're still moving right and we're speeding up. So let's comment on that. Describe the particle motion for this. So we move right, speed up until we are back at the origin. Okay, so what happens when t is larger than this value here? So let's just maybe choose a value higher than it. So we'll go for 6. All right, and let's just see if we can predict what's happening here. So again, what I can see is I'm to the right, so my position is to the right of the origin. I'm going to continue to move right, and it looks like I'm going to continue to speed up because this acceleration just gets higher and higher. So if I bang 6 into it, I should get positive velocity and positive acceleration. All right, so we've got 5, which suggests I'm to the right of the origin. 36, positive velocity suggests I'm moving right. And 24, being positive for the acceleration, means that I'm still speeding up. Okay, so moving right. Okay, and still speeding up. Alright, now invariably if this was the beep test, what would happen is that we'd have another turning point somewhere down here and you continue to go back there. Okay, so this model might be only true for a short segment of the beep test or a run or something like that, that you do some netball training perhaps. Okay, but the model or this cubic function is going to continue to go like this. And you'll know that if I go, come on, speed up, and you're running, if I continue to tell you to speed up, at some point you're going to turn around and go, fair dinkum, Mr. Miller, seriously, I'm going as fast as I possibly can. So the model in real life will only remain true for however long it is true, I suppose. Right, so there you go. That is how kinematics works. Okay, so hopefully you can see the mechanics of it. That is that you know what the functions do. Okay, so we've got our position, velocity, and acceleration functions, and you can interpret what these signs mean. The signs absolutely tell us exactly what's going on with a particle. That's why kinematics and velocity and acceleration give us a lot more detail than just working out someone's speed. If you tell me your speed is 32 k's an hour, that's interesting, I suppose, but the kinematics tell us a lot more about what actually is happening at that point in time.